Good evening, Tiju.
Am I audible?
Yes, yes.
Am I audible now?
Yes, yes, you are.
Hello. Am I audible?
Yes, yes, you are. Good afternoon, everyone. We are at the fourth lecture of our workshop, Initiation into Linear Algebra. Tomorrow we will have Jordan decomposition, Jordan canonical form by Dr. Arindhati. And today we have discussion on Eigenspaces and Generalized Eigenspaces. Dr. Tiju, Cherian John, postdoctoral fellow at Indian Statistical Institute, Delhi, is with us for today's lecture. Dr. Tiju has completed his MSc from the prestigious institution Tata Institute of Fundamental Research Center for Applicable Mathematics in Bengaluru, and he did his PhD from Indian Statistical Institute, Bengaluru Center. His research interest includes quantum probability theory, operator algebras, and operator theory. We are proud that Dr. Tiju is an alumnus of Department of Mathematics at Marthoma College, Tiruvalla, and he took sincere effort to conduct this program successfully. With love and respect, I welcome Dr. Tiju Cherian John to this session.
Thank you.
So we are grateful to all the participants for your patient listening and active participation. We hope it will be beneficial for all of you. I welcome all of you to the lecture. Thank you. Over to Dr. Tiju.
Am I audible?
Yes, you are.
So I am presenting my screen. Just I hope my screen is visible now.
Yes, it is.
Yeah. So today's talk, as you can see, is about eigenspaces and generalized eigenspaces. So without much introduction, I will start. I am very grateful to Marthoma College for providing me good education initially and then inviting me for this program. So let us start. This is, as you know, this is a continuation of the lecture series which has been running through for the past few days. Now let us keep the notations which we were using, as we have been using. V is a finite dimensional complex vector space. Okay, so we are dealing in this lecture. We will be dealing only with complex vector spaces. complex vector spaces of dimension n. Okay, this also I am fixing. Unless I state otherwise, all the vector spaces are denoted by V and dimension is n. And T element of L of V means T is a linear transformation from V to V. So that is the meaning of the word operator. So unless otherwise stated, it will always be from V to V only. And okay, what is the premise of our story? So this program, the general theme of this program is about a deeper understanding of finite dimensional of operators on a finite dimensional complex vector space. So what do I mean by deeper understanding? We will come to know by the end of this lecture. So in lecture 1, you have seen the basic objects of our study, namely vector spaces and direct sums, linear maps, etc. And in lecture 2, you have seen that matrices, how to write a matrix of an operator with respect to a fixed basis. And you have seen that every operator has at least one eigenvalue. Eigenvalue means, I think I don't need to say, if there is a non-zero V, element of V, such that T of V is equal to lambda V for some lambda element of C, then we say that lambda is an eigenvalue of T with eigenvector V. Okay, so obviously in the lecture, this is very, very crucial. One of the cornerstones of linear algebra is this result. Every operator on a complex vector space has at least one eigenvalue. And now, after that, you have seen that in the same lecture 2, you have seen that every operator has an upper triangular matrix. Okay, you know that every operator has a matrix. You know that every operator has at least one eigenvalue. Using this thing, you have seen that every operator has an upper triangular matrix in some basis. And in lecture 3, what you have done is you imposed some more structure onto your vector space. You call it inner product space. And inner product basically gives you a notion of angle, which you have in R2 or C2. Such notions you can generalize using inner product. If you have such a notion, you can find certain operators which are diagonalizable. By diagonalizable, I mean that there exists a basis in which it has a diagonal representation. So in particular, what we have shown is that T is diagonalizable in an inner product space. I mean, by diagonalizable in an inner product space, it will be with respect to an orthonormal basis. Okay, there is an orthonormal basis in which T is diagonal if and only if T is a normal operator. That was what you see yesterday in lecture 3. So let us come back to this lecture. This is what the premise of the story. So now we come back to this lecture, goal of this lecture. So we have seen, or we will see today also, spectral theorem holds good. That means the diagonalization theorem in the inner product space, that is spectral theorem. That holds good when an operator is normal. If it is not normal, it does not work. It is if and only if an operator is diagonalizable in an inner product space using a orthonormal basis, if and only if it's a normal operator. But not all operators are normal and not all operators are diagonal. So, yeah, I have written the definition of diagonalizability if you need. So, even when there is an inner product structure, you don't get diagonalizability always. So, what next? What can you do next? So, when is an operator diagonalizable? So this thing was done in an inner product space. So now, remove the inner product structure. So because in the inner product space also, you could diagonalize only a special class of operators. Only normal operators you could diagonalize. There are a number of operators other than normal operators. How do you deal with them? So otherwise the question is, when is an operator diagonalizable in a general vector space? That is one question which we would like to answer today. And another one, so from lecture 2, you know that every operator admits an upper triangular matrix with respect to some basis. So what is the simplest upper triangular form that can be obtained for T? So what is the simplest upper triangular matrix? So given an operator T, you know that it has an upper triangular matrix with respect to some basis. So can you simplify it further? Can you add more zeros? Can you learn more about it? So that is one of the goals of this talk. Okay, yes, of course it has two parts. The part 1 we will see today, and the part 2, the major thing, is tomorrow's talk, which is Jordan decomposition theorem. So we will see that tomorrow, but we will set the stage for the act Jordan decomposition. Okay, so now we recall some theorems which we had in the from first two lectures. Initially, we have seen a condition that when is a sum of subspaces, suppose you have subspaces of V, U1, U2, Um, when is this sum U1 plus etc. plus U1 is a direct sum, okay? This is a direct sum if and only if, okay? 0 can be written only in one way in a sum U1 plus U2 plus U1. 0, there is only one way to write 0 as a sum U1 plus etc. U1, where each Uj is in capital Uj. And from here, this is an easy exercise from here. I sincerely suggest that everybody should try yourself. I will not do it. If you have subspaces U1, U2, Um, and given that this is a direct sum, then the dimension of the direct sum is same as the sum of the dimensions of corresponding spaces. And I have given hint also. If you want, you can see the YouTube lecture later and pick up with this. And we have also seen that the previous theorem was about having when it is M spaces, how can you say that sum is a direct sum? But if it is only two, there is an easy way also. If it's only two subspaces, if U and W are two subspaces of V, then U plus W is a direct sum if and only if U intersection W is singleton zero. This is an easy way to see whenever we will use these theorems today. And then again, we have seen that if you are given a linearly independent list of vectors with length n is the dimension, okay, then V is equal to n, okay, that we have fixed from the beginning with length n, then it's a basis. Every linearly independent set with n elements is a basis of V. Then we had the fundamental theorem of linear maps, also known as Triangularity Theorem. Dimension of V is nothing, given an operator, dimension of V is nothing but dimension of null space of T plus dimension of range of T. This is what you have concluded the talk with in the lecture 1. And in lecture 2, you have seen the criterion for invertibility of an operator. These three, in a finite dimensional vector space, these three conditions, invertibility, injectivity of the operator, surjectivity of the operator, all these things are equivalent. And also, you have seen that you had seen the definition of eigenvalue, eigenvector, etc. After that, you have seen that if you have distinct eigenvalues, okay, whenever you have distinct eigenvalues lambda 1 up to lambda m, then the corresponding eigenvectors v1, etc. vm, v1 is the eigenvector corresponding to lambda 1, and so on and so forth, so on. Then v1, v2, vm is linearly independent. So eigenvectors corresponding to distinct eigenvalues are linearly independent. This is something again very important for us. And we had seen that when can you say that the matrix of an operator is upper triangular, right? There is an equivalent conditions for that. So what is an upper triangular matrix? This concept is very, very crucial for us. Okay, suppose you have some basis, let's say some basis, let's say v1, v2, etc. Vn is a basis of our vector space V, and suppose you have your operator T as a matrix which is upper triangular. Okay, so that means you have a lambda 1 here, and there are some elements here, but it is 0 here everywhere. Okay, and then you have a lambda 2 in the diagonal, and then something here, and 0, 0 everywhere. Okay, similarly you can get lambda n and something here. Okay, everywhere else it will be 0. This is an upper triangular matrix. So you can see that T of v1 is lambda 1, and T of a vk, if I take here, it will come up to here. This lambda k is here, it will come up to here. That means T of vk is in the span of v1 up to vk. So these vectors, here also we have the basis. Here also we have the basis. This will be v1, this will be v2, dot, 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 up to vn. So this comes here. That means the T of vk is in the span of, T of vj is always in the span of v1, v2, vj. Now, span of v1, v2, vj is invariant under T. These are all same things. Okay, this thing we have to remember. Okay, so this is the crucial thing. if T has an upper triangular matrix, then for each J, T of Vj is in the span up to V1, V2, Vj, and this subspace span V1, V2, Vj is invariant under T for each J. Okay. So this is, next is every operator. This is also a very, very crucial theorem. Every operator has an upper triangular matrix in some basis. This was also done in lecture 2. Okay. So now we start today's talk. So let us begin with some preliminaries. Okay, why do you want to deal with upper triangular matrices, or what are good things about? So what we stopped earlier is every operator has an upper triangular matrix with respect to some basis. So what can you infer from them? What do you gain by getting an upper triangular matrix? So these are easy to deal with. For example, you can determine just by looking at the upper triangular matrix, you can determine whether the matrix is invertible or not, or the operator matrix is invertible and the operator is invertible are same thing. Okay, it's an invertible or not, which just by looking at the upper triangular matrix. How do you see? You just look at the diagonal entries. So T is invertible if and only if each lambda j, the diagonal entries in the upper triangular matrix is non-zero. So how do you prove? These are basic things. I will just maybe give a quick proof. So let us V1, V2, Vn be the basis in which V is upper triangle, T is upper triangular, and assume that diagonal entries are lambda 1 up to lambda n. So first thing we can notice is that T V1 is equal to lambda 1 V1. So here it is V1, V2, etc. you have. So T V1 is equal to lambda 1 V1 we have. And we have assumed that lambda 1 is not zero. Assume that lambda j not is equal to 0 for all j first. Okay. We want to prove that T is invertible. So by doing this thing, you can see that V1 is in the range of T, because T of V1 over lambda 1 is nothing but V1 itself. V1 is in range of T. Secondly, if you consider V2 over lambda 2, okay, so T of V2 is equal to, we know that there is an element here, some element times V1 plus lambda 2 V2. That is what T of V2 is. Therefore, T of V2 over lambda 2 can be written as some complex number A V1 plus V2. Okay. Therefore, we can see that, and this element V1 is already in the range, and this element is already in the range. This element is already in the range. Therefore, V2 is also in the range. Now, you will look at V3. Again, the same way, since we know that the same thinking if you do, T of V3 over lambda 3, we can get it as a linear combination of vectors from V1, V2, V3. So, and also this we have seen already in the range, and this element is already in the range. Therefore, V3 also has to be in the range. By going like this, we can see that each Vj is in the range. Okay. Therefore, what T, if each basis vector is in the range of T, then T is actually invertible. T is surjective. Therefore, it is invertible. And now we prove the other direction. Suppose that T is invertible. You just remember the matrix of T here. Okay. Assume that T is invertible. So then lambda 1 cannot be 0, because otherwise T of V1 is equal to 0. If you take any other lambda j greater than 1, what you can see, and assume that lambda j is equal to 0. Then what we can see, span of V1, V2, Vj is mapped to V1, V2, Vj minus 1. Why? Because lambda j is 0 means what? Your matrix of T, when you write, so the lambda jth column, okay, of the matrix, there is something here, and the diagonal part, okay, diagonal part is 0. Okay, this is the lambda j 0. That means what? T of lambda j, element of the span of lambda 1, etc., lambda j minus 1. Okay, so this full set V1, V2, Vj is mapped into V1, V2 up to Vj minus 1. Therefore, it is not surjective there. If it is not surjective there, it cannot be invertible. Okay, that is the argument there. And so we have shown that T is invertible if and only if the diagonal entries are non-zero. Now another property that we can read off the eigenvalues of T immediately from the diagonal entries. Okay, the eigenvalues of T are precisely the diagonal and diagonal of the upper triangular matrix. So I will not prove this. You can see this later if you want. It's very easy. Just writing as T minus lambda I We have used all and used that this is an upper triangular matrix. When is it invertible? If and only if one of them is 0. Okay. When it is not invertible, if and only if one of them is 0. So only eigenvalues are these. Okay, now let us look at an example. So consider C3 and consider this map in C3. What are the eigenvalues of T? So let us write the matrix of T in the standard basis. Okay, standard basis is the 1 0 1 0 0 0 1 0 0 0 1, that thing. So that is the standard basis. The standard basis, if you try to write, then you get it's an upper triangular matrix. By this, you can see now what you can see. The eigenvalues you can find out 2, 5, 8. Yeah, and also you can see that it is not an it's an invertible operator. Okay. Now, so eigenvalue is something. What is an so V is an eigenvalue if T minus phi. V is an eigenvector. Okay, eigenvector. Eigenvector for the eigenvalue lambda if T of V, Tv is equal to lambda V. Okay. So otherwise we have T minus lambda identity. This operator is not invertible. This is not invertible means it has a null space. So this null space is a very important object which we have. So why am I saying about null space? You will see in a moment. Null space and range of an operator. These are two important subspaces of the operator of the given an operator. You have two important subspaces which are null space and range. Null space is defined like set of all V, Tv is equal to 0. So we know that from the rank nullity theorem, we have dimension of V is dimension null space of T plus dimension range of T. Unfortunately, we don't have V is equal to null space of T direct sum range of T in general. So why I am saying this is important, but this is unfortunate because if V was equal to null space of T direct sum range of T, then I could write the matrix of T. Okay, with respect to this, start with a basis for null space of T, extend it as a basis of null space range of T. Then I can write the matrix of T to be. So in the null space, I will have a big 0 here. Okay, the null space, the operator is 0, and of course it is 0 here also. Null space and range are invariant for T. Okay, so T maps null space to null space, T maps the range to itself also. Okay, therefore I will have a 0 here also, and you have the operator T restricted to U, and you have already, if at all this happens, okay, if this happens, you know that the matrix already has a lot of zeros, and furthermore this operator, okay, this operator is in a smaller dimension. This is living in range of T. Okay, this operator is defined on the vector space range of T. Okay, it is not U actually, it is range of T. Range of T. T restricted to range of T. This is an operator on a smaller dimension space, and furthermore, this will have an upper triangular matrix, isn't it? Because we know that every operator has an upper triangular matrix. So this will further again have an upper triangular matrix. I can choose a basis for range in such a way that this part is 0 and there is something here. So essentially, so I will erase a bit here so that it will be clear. So essentially, if we had null space V is equal to null space T direct sum range T, I could get a matrix with a lot of zeros. You see, only this part you have some elements and everywhere else 0. This is a very nice situation. We can read a lot of information about T from here. But unfortunately, this is not true. And the unfortunate things make our life more interesting. Okay, so define an operator T1 on C2 such that T1 is this operator. Given the matrix of T1 is the standard basis you take, 1 0 is going to 0 0, 0 1 is going to 1 0. Okay, that thing you take, and then the null space and range are both span of E1. E1 is 1 0. Okay, E1 is 1 0. The base is 1 0 basis. Okay. And that you should check. And furthermore, T1 square if you take, null space of T1 square, okay, T1 square is actually 0, and therefore null space of T1 square is equal to C2 itself, and then range is singleton 0. So that we get that V is null space of T square direct sum null space range of T square, because range of T square is anyway 0 only, but here we get fully C. One more example. you take this example in C3, T is defined on Z. T of Z1, Z2, Z3 is 4, Z2, 0, 5, Z3. Okay, Z2 has come here, you should notice that. If you look at this operator, you should verify that null space is this first coordinate and there are two coordinates, this second and third coordinate being 0, that subspace is the null space. And the range of T is this first and third space. Okay, these things you have to verify. In this case, we know that this null space of T intersection range of T is not 0 because you see this Z1 is there in both the things. Okay, so therefore it is non-zero. Now, because of that, by the theorem which I recalled from I think lecture 1, we have null space of T plus range of T itself is not a direct sum because its intersection is non-zero. And furthermore, null space of T plus range of T is not equal to C3, of course, because I know that from here you should verify that. Okay. And now consider T cube. Okay. So if you try to calculate, I'm not doing this calculation because there should be some fun for you people who do this later also. Okay. So if you do this calculation, T cube, if you find, you can find that this will be the value. Now, in this case, null space, it is easy to read off null space from here. This is the first two space. And then range is this space. Okay. Again, we get that C3 is null space T cube plus range T cube. So that is what we previously also we had seen that in this example also, V was, when the dimension was 2, V was null space of T square plus range of T square, direct sum range of T square. When the dimension became 3, we saw an example where null space of P cube plus range of P cube is full C3. And what I want to say is this is not a coincidence. This you will get always. So any n-dimensional vector space you take, null space of T to the power n, direct sum, range of T to the power n will be the full space, and this sum will be a direct sum also. So these are part of an important result which we have. We will prove that now. Okay, so for that I need a few lemmas. Okay, two lemma I need. This is an easy thing to notice. 0. Now T to the power 0 you consider as the operator identity. Okay, so T to the power 0 by definition is identity, and singleton 0 is the null space of that. Now you apply T. The null space is anyway a subspace. It will be always bigger than or is equal to the 0 space. Now you apply T again. So if you apply T again, the null space will not become smaller. Okay, because whatever is in the null space of T, suppose TV is equal to 0, then T into T acting on TV is also 0. Okay, that means T square V is also 0. That means null space will keep increasing only. So null spaces, the sequence of null spaces, if you take like null space of T1, null space of T2, etc., etc., this is a sequence which just keep on increasing. I believe I have convinced you, so I will go ahead without completely proving it. So now, but it cannot grow forever. Okay, this thing cannot grow forever. That is the point. This keeps on increasing, but since we are living in a finite dimensional world, it cannot go on forever. Okay. So null space, so that will come. So initially I will show that if you have some place null space of T to the power m is equal to null space of T to the power m plus 1, then everything else is also same. Suppose you had this equality, then everything else will be also same. That is one thing which we can notice, observe. So what you want to do, this is you take a k and consider T null space of T to the power m plus k, and we want to prove that null space of T to the power m plus k is null space of T to the power m plus k 1 plus 1. So all these things are equal is what I want to show. Okay, from the previous theorem we have one inequality already. Okay, so one containment we have already. Now suppose that we want to prove the other direction. Suppose that V is in null space of T to the power m plus k plus 1. Okay, now V is in the null space of T to the power m plus k plus 1. Okay, we assume that. Now we know that, then therefore T to the power k V, if you apply T to the power m plus 1 there, then this is actually 0. So from there, what you can see, this guy is in the range. He is in the null space of T to the power. T to the power k is in the null space of T to the power m plus 1. Okay. Now, because of that, what you can see is that t to the power m plus k acting on v is, by definition, this is the same. This will be 0 because t to the power m, we have assumed that t to the power m null, okay? Null space of t to the power m is equal to null space of t to the power m plus 1 is our hypothesis, okay? Because of that, now, if t to the power k is in the null space of m plus 1, it will be in the null space of m also, and you get it 0. And thus, we have showed that v is in the null space of t to the power m plus k from this line, and thus we have shown what we have to. Okay, so what I have shown is that in the increasing chain of null spaces, if you have at least one of the two equal, then everything after that will also be equal. So now we can show our theorem, null spaces stop growing. Okay. So that too, it's very interesting to note that null space of t to the power n onwards, it will be same every way. It can be same before also for some operator, but generally we can say that for t with v with dimension n, then null space of t to the power n onwards, it will be same only. So now by the previous lemma, it is enough to show that t to the power n, null space of t to the power n is equal to null space of t to the power n plus 1. If not, what happens? If not, this is not equal. We already have null space t. Here we don't have, okay. This stage, at least one dimension it is there. And up to this stage, at least n minus 1 dimension is there. And here, when we come, it will be at least n dimension will be there. Okay, so it cannot go above that. Okay, so because our dimension is fixed to be n, since all these are strict inequalities, we see that the null space, this inequality cannot hold. This inequality cannot hold. Therefore, they are equal. Okay. Now, this is the thing which I promised earlier. This is not a coincidence. I said earlier that for any operator t with on a vector space of dimension n, you have v is a direct sum of null space of t to the power n plus range of t to the power n. Now, how do we show this? So, since it is only two subspaces, we have noticed that it is enough to show that null space of t to the power n intersection range of t to the power n is singleton zero. This is one of the theorems which I recalled today. It's coming from the first lecture. It is enough to show that, okay? Let v is an element of null space of t to the power n, intersection range of t to the power n. Okay, then we have t to the power n v is equal to 0 because it is null space. Since it is the range of t to the power n, there exists a u in v such that v is equal to t to the power n u. Now, because of that, you apply t to the power n on both sides here. You get that t to the power n v is equal to t to the power 2n u. So, from that, what you get is, to say t to the power n v was 0. So, t to the power 2n u is equal to 0. That means t to the power n u is equal to 0 because we know that null space of t to the power 2n is equal to null space of t to the power n that we have already seen in the previous slide. So therefore, we get t to the power n u is equal to 0. I have written here. Yeah. Thus, we say that t to the power n u is equal to 0. That means u is in the null space of t to the power n. So, but that cannot be true. Therefore, what we have is v is equal to t to the power n u is equal to 0. So, therefore, what we have is the intersection cannot have anything in common. Then we are done actually. Then because it is only 2. So, now this is a direct sum and we are done. Yeah, one more thing I had to say because you want this is a direct sum we have said, but how do you say that it is a full V? It is full V we can say because we know that by triangularity theorem you apply to the operator t to the power n. Dimension of null space of t to the power n plus dimension of range of t to the power n is V. So this is a sum. This sum is a direct sum and the dimension match with the full space dimension. Therefore, we get V is equal to null space of t to the power n, direct sum range of t to the power n. Yeah. So now I come to the second part of my talk where we talk about eigenspaces and diagonalization. Okay, what is a diagonal matrix? I hope everybody knows. Every element except the diagonal entries are 0, except possibly along the diagonal. They are all. That's the definition of a diagonal matrix. Look at an example, and you can diagonal matrices are very nice. You can get almost every thing you want to know about the operator from the diagonal matrix. So obviously upper triangular, so it has a lot of zeros, and the diagonal entries will be the eigenvalues. Okay. Also, these are easy things which you can read off. Okay, now we come to the crucial concept of the eigenspace corresponding to an eigenvalue lambda. Okay, so suppose T is a operator and lambda is, so F is always in. If I write F, this is a typo only. F is always C. Okay, we are considering only complex vector spaces in this talk. The eigenspace of T corresponding to lambda denoted by E lambda T is defined as the null space of T minus lambda I. That means what? Set of all V such that TV is equal to lambda V, isn't it? Okay, this is our null space. T minus, this is the null space of T minus lambda V. And this is a subspace, obviously. I don't have to ask you why it is, because it's already, we are living inside this V only. Okay. Lambda is an eigenvalue of T if and only if E lambda T is, this null space is a non-zero space. Okay. If it is a zero space, then of course it is not an eigenvalue. And now an example again, the same example I think which we saw previously. So what is the EHT? So for this operator, 8 is an eigenvalue, as you know. The eigenspace corresponding to 8 is notated by EHT. This is nothing but the span of V1. This is V1, this is V2, and this is V3. Therefore, this is span of V1 and E5T. Okay, E5T is generated by these two things. So E5T has is the span of V2 and V3. Okay, this is the eigenspace corresponding to 8, eigenspace corresponding to 5. So it can, this is one dimensional here, it is two dimensional here. Okay. Okay. So yeah, you can look at, if you restrict T, if you restrict to E lambda T, that's what I have written, that E lambda comma T, then T is actually nothing but a multiplication by lambda there. Okay, if you have the lambda eigenvalue, if you restrict T to that, this is just multiplication by, this notation is actually multiplication by lambda. Okay. So this is a crucial concept, okay? The eigenspace, if you restrict your operator to the eigenspace, then the operator is just a multiplication. That means V is mapped by T to lambda V for all V element of E lambda T. This is an important concept. Okay. So now we come to the diagonalizability. An operator T is called diagonalizable if the operator has a diagonal matrix with respect to some basis of V. Okay, we see an example first, and this also you have to verify. Consider two bases. Again, the first basis is our standard basis. Second is a chosen basis, a carefully chosen basis for my need. In the first basis, if you look at the matrix of T, it will be like this. But if I write the matrix of T with respect to second basis, that is B prime, you get that it's a diagonal matrix. You can use your tricks and show that this is true. So then T is diagonalizable. Okay. An important concept is, you had in the last class we had seen that, not last class, I think lecture 2 you had seen that distinct eigenvalues, eigenvectors corresponding to distinct eigenvalues are linearly independent. This you had seen in lecture 2. Okay. you can, if you have not seen this, you can go back and watch the video in YouTube, the lecture 2, you will see this. So this is a crucial thing. This will lead us to this important proposition or theorem. Suppose V is a finite dimensional vector space, and suppose that lambda 1 etc. up to lambda m are the distinct. Okay, I am considering all the distinct eigenvalues of T. Okay, then by the way, I don't need it here. Okay, so maybe they are all just distinct. I don't want everything to be counted here. They are distinct eigenvalues of T. Then I can say that the sum, these are all subspaces, so I can take the sum of them. The sum is always a direct sum. Furthermore, this also can be seen. Dimensions, if you add of the eigenspaces, it will always be less than or equal to dimension V. This will essentially fall from the property that sum is a direct sum. We will see the proof. Okay. Now we try to show that this sum is a direct sum. Suppose, and you recall the theorem which I said, a sum is a direct sum if and only if 0 can be represented in only one way. Okay. Suppose that u1 plus etc plus u1 is equal to 0, where uj is in e lambda j. Okay, this is e lambda j t. Okay, there is a typo here. This is a e lambda j t. Uj is there. Then eigenvectors corresponding to distinct eigenvalues are linearly independent, that we have noticed. Hence, each uj is equal to 0. Okay. Because why? Because these are all eigenvectors. These are all in, this is in e lambda 1. That means it's an eigenvector. This is in e lambda m. This is also an eigenvector. So these eigenvectors, if you take, they are all eigenvectors corresponding to distinct eigenvalues. Therefore, what? They are linearly independent. Therefore, their sum cannot be 0. So you get that. Perfect. Therefore, you see that this sum is a direct sum, and now that is the first step. Okay. If you have a direct sum, it is easy to find the dimension of the full space, because in the direct sum, you add the individual sums, you get the dimension. Okay, because there is no intersection, and also, that is a simple property of the direct sum. So because of that, we have proved what we wanted to prove. So basically, we have shown that the sum is a direct sum, and the dimension of the eigenspaces, if you add up, corresponding to distinct eigenvalues, then you get, it will be always bounded above by dimension V. Okay, now I come to the question, when is an operator diagonalizable? So this question is answered by the following theorem. Again, you should recall, this is the most important step here. Okay, this theorem, the sum. Yeah, please. I think it was a disturbance only. Okay, this theorem, you should keep it in your mind that the sum of eigenspaces corresponding to distinct eigenvalues is a direct sum. Okay. So by using this, we will prove what we want. Okay, conditions for diagonalizability. Suppose lambda 1, lambda 2, lambda m are the distinct eigenvalues. Okay, that means I am counting all the distinct eigenvalues of T. Then the following are equivalent. T is diagonalizable if and only if V has a basis consisting of eigenvectors of T. Again, this is equivalent to saying that there exist one-dimensional subspaces u1, u2, un, each invariant under T, such that V is equal to u1 direct sum etc. direct sum un, and fourth one, V is equal to e lambda 1 direct sum etc. e lambda m. This direct sum we can write because of the previous theory. And then the dimension of V is nothing but the sum of the dimensions of the eigenspaces corresponding to distinct eigenvalues. Okay, we will see the proof now. Okay, so 1 if and only if 2 is what we are going to show initially. That is easy, you see. T is diagonalized. Assume that T has a diagonal matrix. Then you know that T of lambda, if V1, V2, Vj is the basis, T of lambda j is nothing but lambda j times Vj only. Therefore, there is a basis consisting of eigenvectors. The same thing, you can see the other way also. So 1 and 2 are equivalent. So now 2 implies 3. What is 2? 2 is V has a basis consisting of eigenvectors of T. And now you want to write 2, 3. Okay. That means you want to show that there exists one-dimensional subspaces. Okay. Each invariant under T such that V is equal to U1 plus etc. plus Un. And again, this is equal to 0. This is easy because you know that there is a basis of eigenvectors. So suppose V1 etc. Vn is the basis of eigenvectors. We are assuming 2. Okay, we are assuming 2 basis of eigenvectors. Then what do you get? Then you get that you take the span of Uj is equal to take Uj is equal to span of Vj. For each j, you take it like that. Okay. Then you can prove 2 implies 3 also. So let us go ahead. We have already seen that. Okay. Now 3 implies 2. 3 means we are assuming that there are one-dimensional subspaces U1, U2, Un for each of them invariant under T such that V is equal to U1 direction etc. Un. Now from here, what you can show? See, what is a one-dimensional subspace? Okay. So Uj is one-dimensional and invariant. Okay. Implies T of U. Okay. So let us take a Uj element of. Let's take a U element of, let's say, some Uj, and T of U then will be is equal to some lambda times U only, isn't it? Because any one-dimensional subspace is this is the only operator on a one-dimensional subspace. Therefore, T of U is equal to lambda U there. Now, so this any element in Uj is an eigenvalue. Therefore, we get that. And since it's a direct sum, we get it's a basis. So you can read it or you can see it later if you want. Okay. Now I am recalling the theorem again. So we have shown that 1 is equivalent to 2 and these 3 are equivalent. So this we have shown. This equivalence of all these things we have shown. And now we want to show that now we will show these 2 are also in the league. How do we show that? We will show that 2 is finally 4 and 4 is finally 5. Okay, let us proceed. So 2 is V has a basis with eigenvectors and 4 is V is a direct sum of eigenspaces and 5 is this one. Suppose that V has a basis consisting of eigenvectors. Then every vector in V is a linear combination of eigenvectors of T. Then we know that V is equal to E lambda 1 T plus etc. E lambda M T. Because every vector in V is a linear combination of eigenvectors of T. That is why I could write this. Now, if that is the case, you get that this is a direct sum itself. Okay? Because this is the only way. This is V has a basis with eigenvectors. Okay? This basis with eigenvectors. With respect to that basis only, I can write any element in V as a sum. And that will be unique only. And therefore, that sum is unique means you get that this is a direct sum. And now 4 implies 5. What was 4? 4 was this thing, right? V is equal to E lambda 1 T direct sum etc. E lambda M T. This implies we want to show that dimension of V is nothing but dimension of E lambda 1 T etc. plus dimension of E lambda M T. That is also easy. And now 5 implies 4 again. Suppose that 5 holds. Dimension of V is given to be dimension of E lambda 1 T plus etc. E lambda M T. Then we already know that the sum of eigenspaces is actually a direct sum. Again, because of that, we complete the proof. We show that V is a direct sum of distinct eigenvalues. From the 5, that also follows. This follows because of this and this. Okay, so now let us look at the theorem once again. This is also very important to understand. So when is an operator diagonalizable? Any of these things is satisfied, any of these conditions are satisfied, then you can say that the operator T is diagonalizable. Okay, so these are the conditions. One of them, if you can check, you can show that it is diagonalizable. And now, if at least one of them does not hold, if you can show that any of them does not hold, okay, if any of these things does not hold, then you can show that it is not diagonalizable. That's the power of this equivalence criterion. Okay, everything is equivalent, logically equivalent. Therefore, if you show one, you show that everything is this is diagonalizable. If at least one of them, if you can show it is not satisfied, then you can show that this is not diagonalizable. Okay, let us go to next example. Okay, example. So consider this map. So what I did in C2, W comma Z is mapped to Z comma 0. Anyways, I am flipping and then I am projecting. So flip it and then project it to the first dimension. That is what I am doing here. So this is not a diagonalized operator. Why? Because 0 is the only eigenvalue here. This you can show. You should show from this line. Okay, don't go to matrix or anything. By matrix also you can show. But to stay with the theme of our program, just show it just by using this equation. Show that 0 is the only eigenvalue, and then also show that the eigenspace corresponding to 0 is nothing but a one-dimensional space. Okay, this is a one-dimensional space. Therefore, C is not a direct sum of eigenspaces, and hence T is not invertible. Okay, we have shown that one of the properties did not hold. Okay, so now we come to the third part of our talk. So third part of the talk is generalized Eigen. So this is the most crucial thing, because for tomorrow's talk, even if you did not understand any of what I said till now, doesn't matter. But this part is more important for tomorrow's talk, and your next lecturer will be using this. Everything which I do here will be used tomorrow. Okay. So now let me go 1 minute. Okay. So we have seen in the previous case, the previous example is an example of an operator which is not diagonalizable. Okay, there are some operators which are not diagonalizable. How do you deal with such operators is the question. As we saw in the previous examples, some operators do not have enough eigenvectors to lead to a good description or using eigenspaces. Why did I say enough eigenvectors? Because that is a condition in the theorem. What is the condition? This is the condition, you see. We should be able to write V as a direct sum of the eigenspaces. Then only an operator can be diagonalizable. Exactly that problem happened here. That could not be satisfied now in our example, this example. Okay, so that is the main problem when we cannot get diagonalizability. Now, this problem arises when, as I said previously, E lambda 1 direct sum, etc. E lambda n is strictly contained in V. Okay, these are distinct eigenvalues. Now, this is what by definition. Just use the definition of E lambda when T, you get this one plus etc. plus null space of T minus lambda m identity is a strict subspace of V. This is the problem. If this is the situation, you cannot do anything. You cannot do diagonalizable. You cannot diagonalize. That is what we know. What more we can do? So let us look at this situation with our existing knowledge. Fix an eigenvalue. Let's say the first eigenvalue we fix. Now we know that even though this is not full, we have assumed this fact. Okay, the null space of T minus lambda I T etc. is strictly contained. But we always know that from our first thing, I think when we started, we talked about this thing. For any operator T, we have V is equal to null for any operator, let's say S. Okay, V is equal to null space of S to the power n direct sum range of S to the power n. This we had proved initially when we started. We proved such a theorem, but we put the notation T there. Okay, now you apply this. Take S is equal to T minus lambda 1 to the power n. Then we know that V can be decomposed, even though we cannot decompose it with direct sums of null spaces. We can decompose at least with the first one you take. You can decompose with direct sum of null space T minus lambda 1 to the power n plus range of T minus lambda 1 to the power n. That we can get. Okay, that's a good thing. But now what else can be done? So now what we are trying to do is, can you decompose this space furthermore? Can you decompose this space furthermore? Because these are all eigen say invariant subspaces. Okay, we will show you will see it in a minute that these are all invariant subspaces. Our aim is to get proper invariant subspaces for T, so that the matrix of T will look similar. That maybe I should say a word or two about that. How will I go back? Yeah. So we are looking for invariant subspaces such that V is equal to invariant subspaces, maybe let's say Uj, such that V is equal to U1 direct sum etc. direct sum Uj. Okay. Why we are looking at that? Because in this case, the matrix of T, if you have U1, U up to Uj are invariant subspaces, the matrix of T can be written. You write a basis of U1 here, so you get something here and a 0 here. You write a basis of U2 here, since it's invariant, it will map only to U2. You get something here, then 0 everywhere else, and etc. You take Uj, you write a basis of Uj here, then you get 0 here. Okay. Everywhere you get 0, and then you have something here. So this is why we are always looking for invariant subspaces. In lecture 2 also we have seen that. So if you have an invariant subspace, enough invariant subspaces, that enough means V is written like invariant subspaces, then you can write the matrix in a much simpler way. You can get a lot of zeros in the matrix. That is why we are looking for invariant subspaces. Null spaces and ranges are obvious invariant subspaces which we can talk about. That's why we are looking at this thing, and I will show you. Maybe I may not prove also, but anyway, this is also an invariant subspace of T. I can show you, maybe I can show you later. This is an invariant subspace of T. This V I am trying to write it as direct sum of invariant subspaces. Okay, so this is one way of writing V as a direct sum of invariant subspaces. So in this case, now, next question is, can I use the other distinct eigenvalue? This only lambda 1 I have used here. Can I use the other lambda j's and decompose this space, okay, as a direct sum of, so let's say, uj's, something like that? Can I do that? This is the question. And that, it will turn out that range of t minus lambda 1 to the power n will be this thing. This is what we are going to show. Okay, so looking at this object is very important. Okay, this now comes the notion of generalized eigenspaces. Now, this object, as you can, this is one positive sign which we got. Forget about this question which I have asked. This is one positive thing which we got. We could write it as direct sum of two invariant subspaces. This is invariant. Please assume it for the time being. I will show it. This we have shown. We know it, and now we are because of that we make a definition. The generalized eigenspace. Okay. If you have lambda as an eigenvalue, then you define the generalized eigenspace corresponding to lambda as the denoted by g lambda t. Write it as null space of t minus lambda I to the power n. Okay. Now this is just a definition, because an obvious thing which you can notice is that null space of E lambda t, which is the eigenspace, okay, is equal to what? Null space of t minus lambda I, okay. This is obviously contained in, because we know null spaces increase, null space of t minus lambda I to the power n, okay. This we know because of the first thing. Initially we had done that null spaces grow. Because of that we know that, therefore E lambda t is always contained in the null space. That shows you can call it generalized eigenspace. I mean, just a terminology, but it makes sense. We will come to that. I'm sorry, just a minute. Okay. So, corresponding that, any element here, I will call it as a generalized eigenvector. Okay. any element in your generalized eigenspace, I'll call it as a eigenvector. Please keep this definition in your mind. This is very important. Okay. And any element in generalized eigenspace is called a generalized eigenvector. Okay. Now, so if you take any v in g lambda t, by definition we know that t minus lambda I to the power n v is equal to 0. So now another thing also we can notice here, v is in g lambda t if and only if t minus lambda I to the power j v is equal to 0 for some j. I mean, why is it true? We know that null spaces, okay, for an operator, yes, null space of t to the power m is equal to null space of t to the power m plus 1, okay, implies null space of this is also equal to null space of t to the power m plus 2, etc. Okay, this is true. Using that, you can show this. I am not showing. This is maybe you can take it in exercise. Very, very simple exercise. Try to do. Okay. This is an if and only if statement. Assume this thing, prove this fact. Then assume this thing and prove the other fact. Okay. This thing I have already told you. E lambda t is null space of t minus lambda I. This is contained in null space t minus because null spaces grow. And this is equal to, by definition, g lambda t. And now let us look at an example. This is the example which we had seen earlier. Okay, the same example I take. Now the question is, find all the eigenvalues, corresponding eigenspaces, and the generalized eigenspaces. You show that C3 is a direct sum of generalized eigenspaces. Okay, I give solution here, but I will not discuss. You can look at the video later and see if you want, but try to do it yourself. So this is crucial. So we had two eigenvalues, and C3 could be written as the generalized as the direct sum of generalized eigenspaces. So eigenvalues were 0 and 5 only. Okay, and C3 could be written as the direct sum of generalized eigenspaces corresponding to the distinct eigenvalues, which are 0 and 5 in this case. And again, this is a general thing. So to move towards that, so this is the analogous theorem. You know that this eigenvalues, eigenvectors corresponding to distinct eigenvalues the eigenvectors corresponding to distinct eigenvalues are linearly independent. This you know, okay. Now this is the analogous fact, okay. This is analogous fact for generalized eigenvectors. Suppose you have lambda 1, lambda 2, lambda m are distinct eigenvalues of t, then you get corresponding generalized eigenvectors are linearly independent. Please look at the definition of eigenvalues, generalized eigenspace and eigenvector once again, because this we will use when we prove anything with this, okay. The g lambda t is null space of t minus lambda I power n, and any element here is called a generalized eigenvector. Okay. So this is the corresponding. These are the analogous fact. Okay. Okay. Let us prove this. Suppose a1, a2, am are complex numbers such that a1, v1 plus etc. am, vm are is equal to 0, and these are all distinct. These are all generalized eigenvectors, okay? So that means what? We have Vj is an element of G lambda j t. This we have to keep it in mind, okay? These are corresponding to distinct eigenvalues, generalized eigenvectors. We want to show that they are independent. And in this case, let k be the largest non-negative integer such that t minus lambda 1 to the power k v1 not is equal to 0. Okay, k can be 0 also. That means if k is equal to 0, what we get? K can be 0 also. That's what I'm saying. What we know is that t minus lambda 1 identity acting on v1 to the power n is equal to 0. We know. Okay. We have taken a v1 is a non-zero element. We have taken v1. Vj is non-zero. Okay. Vj is non-zero I have taken, and Yeah, so basically I'm sorry, one thing I have to add. When I say that generalized eigenvectors corresponding to distinct eigenvalues are linearly independent, I have to write non-zero, okay? Distinct eigenvalues and we are corresponding generalized eigenvalues, non-zero generalized eigenvalues, because zero is also a generalized eigenvector corresponding according to our definition, but always we should work with non-zero, okay? This thing should be included in the statement because of the definition which I have given, okay? Then only you get the theorem, otherwise there is no theorem here. Okay, so we have taken non-zero generalized eigenvectors. Okay. Now, let k be the largest non-negative integer such that t minus lambda 1 to the power k v1 is not zero. Okay, let w is equal to that element. W is a non-zero thing. Now, t minus lambda 1 w is equal to, you apply t minus lambda 1 here, this is obvious, this is equal to 0. That means w is in the null space, isn't it? That means what? Tw is equal to lambda 1 w. That means w is an eigenvalue. Now, because of that, t minus lambda w, for any lambda you take, okay, any lambda in C you take, t minus lambda 1 w, lambda w is nothing but lambda 1 minus lambda w. This is directly from this equation. Therefore, what we get is t minus lambda 1, lambda to the power n w is lambda 1 minus lambda to the power n. You apply 10 times, this happens n times, okay, times w, okay. N is a dimension which we have already fixed. Apply this operator. Now you define this operator, t minus lambda 1 to the power k, and first thing, lambda 1 you take that k, and lambda 2 onwards you take n only, okay. This operator you consider. Yeah, you apply it on the both sides of this equation. This is the equation which we started with. Our aim is to show that these people are linearly independent. Okay. So, if you apply this operator to the both sides, we get 0 is equal to a1 and v1, you act this operator on v1, and then you have to act this operator on v2, etc., etc. But what happens is that t minus lambda 2 to the power n acting on v2 is equal to 0. Okay, there is a term t minus lambda 2 to the power n in my operator. Okay, because when you act on both sides here, you get that this is nothing but acting is on the first vector only. Okay, but first vector, then what is t minus lambda 1 to the power k acting on v1? Okay, that acting on v1 is our, by definition, our. Go to the next slide. Yeah, that means that 0 is equal to this thing, a1 lambda 1 minus lambda 2 to the power n, etc. Lambda 1 minus lambda n to the power n. Because we also noticed in the previous stage that p minus lambda to the power n, w is always lambda 1 minus lambda, lambda 1 minus lambda to the power n w. That is what we have seen with, that is the property of w. Because of that property, we get that this is all becoming k lambda 1 minus lambda 2 to the power n, etc. Lambda 1 minus lambda n to the power n acting multiplied with w. So, what we get from here, okay, this can be zero. These are all non-zero. We took only distinct eigenvalues, isn't it? Huh? We started with distinct eigenvalues. Because of that, this is non-zero, and all these terms are non-zero because lambda j's are distinct. And now we also know that w is also a non-zero thing, and therefore, if you want to get 0 on the left side, this must be equal to 0. a1 has, because this is non-zero and none of them are 0. Because of that, now a1 has to be 0. Similarly, now, so we have shown that a1 has to be 0. The same steps, the same step you do with w is equal to t minus lambda 2 identity to the power k. K should be the largest non-negative integer such that lambda 2, you replace lambda 1 with lambda 2 and do the same thing. Okay. Then you see that a2 will also be 0. In that way, when you proceed, we get that all these terms, scalars, should be 0. Hence, we get that these are linearly independent. Okay. Now, this is the thing which I was saying. If you take any polynomial p, okay, So P is a polynomial means that summation z to the power j, maybe alpha j, okay, alpha j element of C, alpha j element of C. So P of z is this one. If you have a polynomial like this, finite, okay. So let's say some k, j is equal to 1 to k. Any polynomial you take, now consider the operator P of t. If P of z is this one, P of t, by definition, I define P of t is equal to summation alpha j times t to the power j. For any operator t, I can define P of t just using these coefficients, okay. J is equal to 1 to k again. So what this lemma says, this is essentially a lemma, which says that if you have any operator t and for any polynomial with complex coefficient you take, then we know that P of t and range of P of, this is very powerful. Even though it's a small lemma, it's a very, very powerful theorem. And the null space of P of t and range of P of t both are invariant spaces for t. I have told, null space of t minus lambda j to the power n is invariant. Invariant for t. I had asked you to assume this thing in the beginning, some time back, but the reason is the following. This is a polynomial, right? T minus lambda j to the power n is a polynomial of t. So this is P of t, where P of z is equal to z minus lambda j to the power n. This polynomial, if you take, you can see that P of t is this operator, and null space is invariant for t. This null space of P of t and range of P of t are invariant. I think I am running out of time. Let me see. Okay. Suppose how to prove this? Suppose V is in null space of P of t, and then P of t is V is equal to 0, obvious, and then you can do this computation. P of t acting on TV is equal to t acting on P of t, because it's always only t is there. Summation alpha j P of summation alpha j t to the power j and t. These two commutes. Okay, t you can write here or t you can write here. These two commutes. Therefore, this will be like that. Therefore, this is what? If you have V from null space of P of t, this is t of 0. This is which is equal to 0. Therefore, we have shown that null space of P of t is invariant for t. A similar thing we can show for the range also. Okay, suppose V is in range of P of t, then there exists U in V such that V is equal to P of t. Maybe I'll skip this. Again, a similar and symbol computation. You can notice this. All the thing for the time we are using only the commutativity of commuting, the property that P of t and t commutes. So keep it in mind for any polynomial on earth you take with complex coefficients, null space of P of t and range of P of t are invariant under t. Very, very powerful lemma. Okay, now we come to our main goal of this lecture. I have to spend some time here. Okay. Suppose V is a complex vector space and T is a operator there, and lambda 1 etc. lambda n be the distinct eigenvalues of T. Then V is a direct sum of the G lambda j T. Okay, so I have already told that G lambda j T is equal to null space of T minus lambda j identity. Always this identity will be there when I write T minus lambda, even though I forget, to the power n. Okay, this is, as I said, this is an invariant sub. Because of the previous lemma, this is an invariant subspace for T. Okay, so this is the first thing is that V is written as a direct sum of invariant subspaces. So I had showed you earlier that what is important about invariant subspaces. If you have enough invariant subspaces, somewhere I had written, maybe, yeah, here. If you have enough invariant subspaces, you get a nice description, okay, for the operator. This is what we are looking for. So that is what this theorem gives us. If you have the generalized eigenspaces corresponding to the distinct eigenvalues, then you have V as a direct sum of the generalized eigenspaces. And furthermore, this is the previous theorem. Okay, this we have already proved. We have already proved that G lambda j T is invariant in T. And next, T minus lambda j restricted to G lambda j T is in nilpotent. So this both are same. Why is nilpotent? By nilpotent I did not define here. S is nilpotent, called nilpotent if what s to the power k is equal to 0 for some k. Some k element of n. Okay, this is the definition of nilpotent. So t minus lambda j restricted to g lambda j is a nilpotent operator. Why? Because g lambda j is nothing but the null space. Again, look at the definition of g lambda j t. This is directly from the definition. Okay, it's equal to null space t minus lambda j to the power n. This is the definition of g lambda j t, and hence t minus lambda j, okay, to the power n on this space is actually 0, okay, because it's a null space. So we already have these two things. The only main thing to show is that V is a direct sum of g lambda j t. Okay, let us, this is I think about the first things. There's 2 and 3, yes, 2 and 3 follow from, essentially from definitions and the previous lemma. Okay, now we try to prove the first. Okay, what we have to show, we have to show that this direct sum is complete. This direct sum completes V. It's just a okay, we prove it by induction. Okay, let us take this, I think, a little long proof. Let's see. Proof is by induction. Let n is equal to 1. Then t is equal to lambda v. Tv is equal to lambda v. Okay. Lambda v for some lambda element of C. Then g lambda t is nothing but the null space of t minus lambda. Dimension is 1 here. Okay, is equal to v. So when n is equal to 1, we get what we want. So recall again what we want. We want to show V is a direct sum of g lambda t's and corresponding distinct eigenvalues. So when that one dimension there is only one thing, then you have the theorem. Assume that n greater than 1 and the desired result holds for all vector spaces of smaller dimension. Okay, this is the induction hypothesis. Since V is a complex vector space, T has an eigenvalue. Okay, so since that we have seen in the lecture 2, since T has an eigenvalue, we always have a general G. There is a lambda, right? Isn't it? Huh? So therefore, there exists G lambda 1 T. Etc. There are some eigenvalue. At least one is there. Therefore, there is at least one eigenspace is here. And of course, let's see. Therefore, this M. This m here, this m is greater than or equal to 1 is what I have showed first because there exists an eigenvalue. Okay. Now, if it has an eigenvalue, then we can write. We know that this result is V is equal to null space of t minus lambda I to the lambda 1 to the power n direct sum range of t minus lambda 1 to the power n. This is the first thing which we proved today. So, by using that, we write V as a direct sum like this. Okay. Now, take P of z is equal to minus lambda 1 to the power n. We see that both, this is already invariant, we know. U is the range of this thing. Therefore, this is also invariant subspace. So, already we have got one such step. Now, because G lambda 1 T, okay, lambda 1 is an eigenvalue. This has dimension at least 1, okay. Therefore, this is a non-zero vector space. Because of that, this U has dimension strictly less than n, okay. So, if you recall, this was the similar way we had proved the upper triangularization in the lecture 2. In the lecture 2 also the idea was the same. To prove that every operator T has an upper triangular matrix, what we did was first we showed that every operator in one-dimensional space has upper triangular matrix. Then you apply induction. Okay, same way we are trying to do here. The same, you should go back and compare these two proofs. Okay, yeah. So therefore, the dimension of U is strictly less than n. Thus, we can apply our induction hypothesis to T restricted to U. So, T restricted to U is an operator from U to U because U is invariant. This is what the meaning of invariant subspace. Okay, this is an operator on its own right. Okay, none of the generalized eigenvectors of T restricted to U correspond to the eigenvalue lambda 1 because if at all there was a lambda eigenvalue lambda 1 was coming in here, it would have always gone back to the G lambda 1 P. Okay, this would have gone back to here. Therefore, lambda 1 cannot be an eigenvalue of T restricted to U. Okay, because T on U is nothing but T restricted to U. Now, each eigenvalue of T restricted to U is lambda 2 etc. lambda m because what T on U is actually equal to T restricted to the operator T restricted to U. This map U to U because now if at all some eigenvalue is there for T, that will be the eigenvalue of T restricted to U also. I mean, T from the space U, okay? From the space U. Eigenvectors from the space U will be eigenvalues for this also and vice versa. Therefore, these are the eigenvalues of T restricted to U. And by the induction hypothesis, we assumed that U is the T restricted to U is acting on a smaller vector space. Now, by induction hypothesis, we have this one. Now, we have this one, and now you know that V is equal to G lambda 1 T direct sum U. That is the previous thing which we had earlier, okay? This is where we started. V is equal to V lambda 1 T direct sum U. So, because of that, now we can complete the proof if we show that, see, this U is already written like this. We only need to remove this restriction thing, right? If you remove that restriction thing, we are done. Okay. Yeah, if we show this line, V lambda K T restricted to U is equal to G lambda K T, we are done because of this fact and this fact. Fix K, we take one of them, okay? And the inclusion is, this one is obvious, okay? G lambda K T restricted to U is contained G lambda K T. Because if you take any generalized eigenvector here, this will be a generalized eigenvector here also, okay? To prove the inclusion in the other direction, suppose V is in G lambda K T. Okay, we take a V here. Okay, then what we get? Okay, now write, because you know that V is equal to G lambda 1 T. Sorry. G lambda 1 T direct sum U. We know that this V can be little v in capital V can be written as, any little v can be written as V1 plus U. Okay. So where V1 is equal to G lambda 1 T and U element of U. Now, our induction hypothesis says that. Capital U is a direct sum of the eigenspaces. Because of that, I can write U is as a direct sum of generalized eigenvectors, non-zero generalized eigenvectors of T restricted to U. Okay. Now, therefore, we get from this equation that V is nothing but V1 plus etc. plus Vm. Now, because generalized eigenvectors corresponding to distinct eigenvalues are linearly independent, these are all generalized eigenvectors corresponding to distinct eigenvalues, okay? Independent, the equation above implies that Vj equals 0 except possibly from j is equal to k, okay? This fact, just think a bit there and convince yourself, okay? And now, in particular, we see that V1 is equal to 0, thus V is equal to U element of U. So, because V was initially assumed to be like this, V1 is equal to 0 we got, therefore we see that V is equal to U itself. V was taken from here only, you see, V was taken from G lambda K T, okay? And since V is in U, we can conclude that this is here only, okay? So, we are done. So, we have proved a very, very powerful theorem. Okay, so what is the theorem? Once again. Yeah. So, this is the best we can get for the time being. Okay, for the time being, we see that V can be written as a direct sum of invariant subspaces for T. And on each invariant subspaces, this operator, T minus lambda J, is a nilpotent operator there in each of the invariant subspaces. Okay, let us, now you see that there exists a basis. So now you can find a basis for G lambda 1 T, G lambda 2 T, etc. You find a basis for each of them and then put these bases together. We get a basis for V itself. Okay, so that is, and that is called the basis of generalized eigenvectors. So V has a basis with generalized eigenvectors. Okay, so that is our next theorem. So, sorry. Okay, T element of V, then there is a basis of V consisting of generalized eigenvectors. I already told that. So start with choose basis for G lambda J T. Okay, for each generalized eigenvalue, consider the generalized eigenspace. Choose a basis. Since it's a direct sum, you put together, it becomes a basis of T. Okay. So now let us recall this theorem and let us try to write the matrix. Okay, we have the theorem here again, and let us try to write the matrix of T. Let us try to write the basis of matrix of T minus lambda I. Okay, let's see. Wait. Okay. T. Okay. T minus lambda 1. Okay, this operator, if you take this operator, if I take, it will have the first. You consider that I am going to write a basis with respect to this one. Okay. So we have G lambda 1 T here, etc. G lambda K T here. Okay. This operator, you see, there is something here, and everything else is 0. Okay. So similarly, I can write, and there is something here. Similarly, I can write for each lambda j. There will be something in here, and everything else will be 0. Okay. So let me write one more thing. Because of this, now what we have is, look at the matrix of T, okay? The matrix of T will be in this basis, okay? You start with this basis. What is here? G lambda 1 T. This is a null space of T minus lambda 1, lambda 1 T. So there you have, on the diagonals, you have lambda 1, etc. And there is a operator here, okay? Something here, there is something here, and 0. This is the first thing, lambda 1 G, lambda 1 T. And now take the G lambda 2 T part, okay? Here again, we have lambda 2 here, okay? Up to the dimension lambda 2, and there is something here, 0, 0, 0. And again, you do the same thing. So this part, this part is nothing but T minus lambda j restricted to I. That is this part. This part is T minus lambda 2 restricted to G lambda j T. So this is a nilpotent operator. So at the end, what we are getting is the matrix of T is equal to sum of some lambda j times some identity matrices of the appropriate dimension, okay, plus a nilpotent matrix. This is what matrix of T, we get it like that. So we can look at the matrix of T on G lambda j T, okay. We have T is equal to lambda j plus nilpotent. T restricted to G lambda j T. This is the crux of this theorem, okay. So now what we have is what we have done till now, what we have done today. First case is, how do you distinguish diagonalizability? What can you say in the general case, okay? Consider then when T is diagonalizable, we see that D has a basis of eigenvalues of T. In the general case, we know that D has a basis of generalized eigenvalues of T. In the diagonalizability, we know that V is the direct sum of eigenspaces. If it is not diagonalizable, in general, we get that V is the direct sum of generalized eigenspaces. Now, dimension of V is what? Dimension of V is direct sum of the dimension of eigenspaces. In the diagonalizable case. In the general case, we get that the sum of the dimensions of generalized eigenspaces. Now, T restricted to your eigenspace E lambda 1 T is nothing but multiplication by lambda K there, because it's an eigenspace. Similarly, T restricted to G lambda K T is nothing but the multiplication by lambda K plus a nilpotent operator. That is what I tried to explain here. This theorem, if you understand, that is what. So, we get the conclusion of this talk is that when it is not diagonalizable, you can get this. Similar to what we had here, but with generalized eigenvalues. So maybe I will stop here. You should understand all these things before attending tomorrow's lecture, because you are going to heavily use this thing. Now the thing is, you see, matrix of T, as I said, is nothing but this lambda j plus nilpotent in each of the blocks. Okay, here you have lambda j plus thing. In each of next block also you have the same thing. Like that you have. Now, what can you do on a nilpotent operator? How to simplify a nilpotent operator? That is what Jordan decomposition theorem is. So, Jordan decomposition theorem is just about simplifying the nilpotent operators and find how T looks like at the end. So, if you write at the end, it will be just an upper triangular matrix with the diagonals having the eigenvalues and the line above the diagonal. These lines will have some ones. That is what at last we are going to get. Okay. So thank you. So I am done.
Time for discussion. If anyone have any question, again. There is one question in the chat box.
Yeah.
If T is diagonalizable, will generalized eigenspace and the eigenspace of T coincide?
Exactly. That is the case. With that you can see directly from the definition itself, okay? Huh? This thing here and this thing will be same if T is diagonalizable. Yes. Just look at the definitions only, okay? Null space of T minus lambda j. They always go back to the definition T minus lambda j I to the power n. Okay, just go back to this definition. Any other question? So I am seeing a question in the chat box like difference between generalized eigenvalues and eigenvalues. Okay, as that we have already seen. Generalized eigenvalues and eigenvalues. Yeah, generalized eigenvalues and eigenvalues. So for eigenvalues, we have T of V is equal to lambda V. This is eigenvalue. Generalized eigenvalue does not give you that, but we get that T minus lambda I to the power n acting on V is equal to 0. This is eigenvalue. This is generalized eigenvalue. So any other question?
Sir,
Yeah, please.
so what is the application of eigenvalues in real life, sir?
So eigenvalues is a thing which is you are applying every time you do a Google search, for example, and it is all over the universe. So maybe on Friday, on Saturday stock, on Saturday stock, it is completely about this, how to use these things. Okay, so it's all over the world. Google search, you try to do image compression, you do quantum mechanics, quantum information sciences, everywhere. So you will see more about it on Saturday. Okay, you can see precise things on Saturday.
Okay, sir. Thank you, sir.
Any more questions? I think there is no more questions. Okay. I think it was a very good session. All the participants will get benefit from the lecture. The lecture is available in the YouTube. So anytime, whenever you want, you can go back and watch the lecture. So simply, Dr. Tiju was doing a superb job. Every idea was very clear, and I think all the participants really enjoyed the lecture. So, on behalf of Department of Mathematics, I express our sincere gratitude for this superb lecture. Thank you, Tiju.
It's a pleasure to talk. Thank you.
And I thank all the participants for your patient listening. Tomorrow we'll be joining back at 3:55 p.m. For the talk on Jordan Canonical Form by Dr. Arundhati Krishnan. Thank you all. We'll meet you on tomorrow, 3:55 p.m. Thank you.